everyone, welcome back to another video. So today I'll be going through force of friction calculations, just some various examples and practice problems. So let's go ahead and get into our first example. In this problem, Ryan is walking to pick up his Starbucks order but does not realize that the person in front of him has spilled her iced latte. As Ryan, who has a mass of 65 kilograms, steps in the latte, the coefficient of kinetic friction between Ryan and the floor is suddenly reduced to 0.040. What is the force of friction between Ryan and the slippery floor? So as per usual, the very first step that I like to do is identify the givens in the problem. So the very first number that I see is that Ryan has a mass of 65 kilograms. I'm going to go ahead and record that. So G is for given, mass is 65 kilograms. As I continue to read, it says that the coefficient of kinetic friction is 0.04. Okay, so I'm going to write that coefficient of kinetic friction. The symbol for that is the Greek letter mu, and it's going to be 0.04. The other thing that you can draw for givens is the free body diagram. So with any force problems, the first thing you might want to consider after writing your givens is drawing a free body diagram to better visualize the scenario. So obviously Ryan has a mass and he's on Earth. That means that gravity is going to be acting on him. So gravity always points downward toward the center of the Earth. That's going to be the force of gravity. And since Ryan is not accelerating vertically, then we know that there has to be a vertical force in the upward direction that opposes gravity. In this case, it would be normal force because Ryan is on the Earth and the Earth is a surface pressing back up on him. Now, because he's not accelerating vertically, you know that these two forces have to be equal in magnitude. Because Ryan is slipping, that means that there is actually a force that's acting horizontally, and this is just going to be due to the force of friction, which is what we're going to be solving for. So let's go and write that down, force of friction. So just to clarify again, our unknown is going to be the force of friction. Okay, so what equation are we going to use to solve this problem? So the equation we're going to use is simply the equation for the force of friction, which is that the force of friction is equal to the coefficient of friction times normal force. Now for this scenario, we know that the normal force is actually equal in magnitude to the gravitational force. I'm going to highlight that in green over here. You can see that they are equal to each other. So I can actually replace this normal force with the force of gravity. So F friction is equal to mu times, again, when I'm talking about the force of gravity replacing it, I'm just talking about the magnitude of the force of gravity, because normal force and force of gravity, again, they're equal. I'm going to write that over here. Normal force is equal to the force of gravity. They're the same in magnitude, just opposite in direction. How do we solve for the force of gravity? Well, we solve for the force of gravity by multiplying mass times the acceleration due to gravity. And again, I only care about the magnitude, so I'm not going to worry about the fact that the acceleration due to gravity is negative. I'm just going to use the number, and we'll deal with direction later on. So force of friction, therefore, if I substitute everything in, is going to be equal to mu, which is 0.04, times the mass, 65, times gravity, 9.8. If I simplify that further, I will get 0.040 times 637. And if I simplify that further, the answer is going to be that the force of friction is equal to 25.48 newtons. Now I'm going to refer to my free body diagram, and it looks like the force of friction, which is what we're solving for, is moving in the rightward direction. So let's go on and solve the second problem. The second problem is very similar to the first one. So here's a scenario. Unbeknownst to students, every time the floor of the commons is waxed, Dr. Rafter likes to slide across the floor in his socks. Dr. Rafter has a mass of 80 kilograms and the coefficient of kinetic friction between his socks and the floor is 0.120. What is the force of friction that opposes Dr. Rafter's motion? So again, our first step is to identify our givens. So we have, again, the mass of Dr. Rafter, 80 kilograms, and we have the coefficient of kinetic friction over here is going to be 0.120. Let's write those down. So just to review, givens, mass is equal to 80 kilograms, and our coefficient of kinetic friction, which is mu, is 0.120. Let's go ahead and draw the free body diagram for this scenario. So there's Dr. Rafter. He is our system under study, which is represented by the box. He has a mass, so he's obviously going to have a force of gravity acting on him. Since he is on a surface, that means that the surface is pressing back on him, and we have a normal force. which is going to be equal in magnitude to the force of gravity. So he's sliding and the force of friction is acting on him as he's sliding across the floor. And what it's actually doing is it's probably going to be slowing him down. He initially slides, and as he slides, the force of friction is acting on him because when he's sliding, he's obviously not importing any more force. The only force that's acting on him now is the force of friction opposing his motion, working against his motion. So my unknown in this situation is still the force of friction. And the equation I'm going to use the exact same equation, which is that the force of friction is equal to the coefficient of friction times normal force. Just like last time, we know that the normal force is equal in magnitude to the force of gravity. So I can replace that normal force with the force of gravity. In other words, I can say that it's equal to mu times mass times acceleration due to gravity. Again, we're just going to be focusing on the magnitude of gravity and not the direction, because we can just refer back to our free body diagram for direction in the end. And I'm going to go ahead and substitute everything. So my force of friction is equal to mu, which is 0.120, times the mass, which is 80, times the magnitude of the acceleration due to gravity, which is 9.8. And if I calculate that out, it will end up being 0.120 times 784. And if I simplify that further, it will give me 94.08 newtons. And again, I drew my force of friction in the rightward direction. All right, awesome. So that's the second problem. Let's go ahead and work on another one. So in this scenario, we have Carl and Russell, and they are trying to make their 30-kilogram dog, Doug, go out the back door, but Doug refuses to walk. If the coefficient of kinetic friction between Doug and the floor is 0.5, how much force should Russell use to push Doug at a constant speed? Okay, so let's go ahead and highlight some givens and also some important information from this scenario. So the first thing I see is that the dog is 30 kilograms. That's a mass, okay? The next thing that I see is that the coefficient of kinetic friction is 0.5, so that's mu. And the last really important piece of information, which I'll highlight in pink, is that Doug is being pushed at a constant speed. So constant speed implies that acceleration is equal to 0, and that means that F net is also going to be equal to 0. In other words, all of our forces are going to have to cancel out. So let's go ahead and list this and draw our free body diagram. So I'm given the mass of the dog is 30 kilograms. I also know that the coefficient of kinetic friction is going to be 0.5. And I know that acceleration equals 0. And so I'm going to actually have that situation show up in the free body diagram. I will list that F net equals 0 though. Okay, let's go ahead and draw the free body diagram. So Doug has some mass and he's on Earth, so he has the force of gravity. Doug is on the ground, that's where he's getting pushed, so there's going to be normal force. Since Doug is not accelerating vertically, I know these two forces have to be equal in magnitude. We know that Doug is being pushed, so there's going to be F applied. And then there's going to be force of friction acting against Doug's motion. So if F applied is going to the rightward side, then force of friction is in the leftward side. Now, because Doug is being pushed at a constant speed, that means that there is no acceleration. That means that there's no net force, and all of our forces have to be balanced. So F applied is going to be equal in magnitude to the force of friction. So let's go and talk about our unknown. Our unknown we're trying to solve for is F applied. However, we can solve for the applied force by solving for the force of friction, since in this scenario, Doug is being pushed at a constant speed, which means that there is no acceleration on this system, and also the net force is equal to 0. So all the forces have to balance and cancel out. That means that in the horizontal direction, F applied in the rightward direction has to balance out with the force of friction acting against it. They have to be equal in magnitude and therefore be able to cancel out. So that means that our equation we're going to use would be for the force of friction, because once you know the force of friction, we can solve for the applied force. So I'm going to write that F applied is equal to the force of friction, and the force of friction is equal to mu times the normal force. I'm gonna go ahead and bring this over to this side. So force of friction is equal to mu times, instead of the normal force, just like last time, we know that in this scenario, normal force and the force of gravity are equal in magnitude. So I'm going to replace normal force with the force of gravity. And it's going to be, again, solved by multiplying mass times the acceleration due to gravity. And then now I can substitute. So we know that mu, or the coefficient of friction, is 0.50. The mass is 30, and gravity is 9.8. So if I continue to solve this out, I'm going to get 0.50 times 294. And then the force of friction as our final solution over here is going to be 147 newtons. And just to include direction, in our diagram, it is going in the leftward direction. Perfect. Let's move on to our next problem. This one's a little bit different. So Katie is redecorating her room and wants to move her 60-kilogram desk closer to the window. She determines she needs to push with 320 newtons in order to overcome static friction. What is the coefficient of static friction? Okay, so let's start by highlighting our givens. I know that the desk is 60 kilograms. I know that she needs to push with 320 newtons, and she is overcoming static friction. That's something I'm going to highlight in pink. Kind of a read in between the lines situation. Okay, so the two numbers, let's address those. The first one is obviously mass because it's kilograms. So we know that the mass is going to be 60 kilograms. The second thing I see here is she needs to push with 320 newtons. That push tells us that this is F applied. So F applied is equal to 320 newtons. And if we're saying we're overcoming static friction, that's the point, that's kind of like the tipping point between not moving and moving. So when you're overcoming static friction, that means that your net force horizontally at this point in time is equal to 0. Because if it's any greater than 0, that means that it's going to be accelerating in one direction. If it's any less, it's accelerating in the opposite direction. And so if you're overcoming static friction, it's just that tipping point before it's any value outside of 0, it's got to be 0. So let's draw this diagram. If F net equals 0, that means that it's going to be a free body diagram that has balanced forces, but it's good to visualize regardless. So her desk is going to have a force of gravity acting on it because it's a mass, it's on Earth. Because this desk is on the ground, then we're going to have the normal force pushing up on the desk. And these are going to be equal in magnitude and opposite in direction because they'll cancel out and this desk is not accelerating vertically. There's obviously going to be an F applied because she is pushing this desk. And the F applied is going to be equal to 320 newtons. And then her frictional force is going to be actually the same value, 320 newtons as well, because F net is equal to 0, so F applied has to equal force of friction. My unknown in this situation is the coefficient of static friction. That's what we're trying to solve for. Okay, so we're trying to solve for U, or mu. Okay, so our equation that we're going to use is, well, there's kind of two things going on here. One is our understanding that F applied is equal in magnitude to the force of friction because based off our free body diagram and based off this scenario, we know they have to be equal in magnitude. The other equation we're going to use is the equation that we're learning, which is that the force of friction is equal to mu times the normal force. I'm going to bring this over to this side and continue working here. So I'm going to actually replace force of friction here with F applied. We kind of already did that in our free body diagram. We have to know that they're the same value because they are equal to each other. So I'm going to say F applied, or the value of F applied, which is really just the force of friction as well, as seen from our free body diagram, is equal to mu times the normal force. F applied is then equal to mu times, like we were saying in our previous problems, for this situation for this desk that is just horizontal on the ground, the normal force is just equal to the magnitude of the force of gravity. We can also visually see that in our free body diagram. I can go ahead and highlight that for you too. And then I'm going to replace the force of gravity with mass times the acceleration due to gravity. And now we have everything that we need to substitute and solve for the unknown. So I'm going to substitute F applied is 320, mu is our unknown, the mass is 60, and gravity is 9.8. What I need to do is divide both sides by 60 times 9.8. Okay, which really is just mu is equal to 320 divided by 588. And mu is really just equal to 0.54. Remember that the coefficient of friction, whether it's static or kinetic, doesn't matter. These coefficients, they don't have any units, so that's perfect, 0.54. All right, on to our last question here. So Ellie is pushing her 1.2 kilogram walker across the floor with 10 newtons. There is a coefficient of friction of 0.5 between the walker and the floor. What is the net force? Let's go ahead and highlight our givens. So there's one thing here, kilograms, that's going to be a mass. That's the mass of the walker. She is pushing with 10 newtons. I'm going to go ahead and draw this line between the word push and this 10 newtons. I know that's going to be F applied. And then we have a coefficient of friction, which is going to be 0.5. We're trying to solve for the net force. All right, let's identify our givens and draw this scenario. So we have a mass, which is 1.2 kilograms. We have F applied is equal to 10 newtons. We have a coefficient of friction is equal to 0.5, and we're trying to solve for F net. So if I was to draw this free body diagram, again, this object has the force of gravity acting on it because it has a mass and it's on Earth. Because her walker is on the floor, there's going to be a normal force pushing back up on the walker. And these two forces are going to be equal in magnitude and cancel out since the walker is not accelerating vertically. There's going to be F applied. And then the force of friction is acting against. I'm just going to assume because her walker is going forward, that friction will be less than F applied, but we'll obviously find that out when we're solving this problem. Okay, so the equation we're going to use is going to be actually kind of two things. One is our understanding of what F net means, and the other is going to be obviously the force of friction is going to be part of this equation. So start with the more general one, that F net is equal to the sum of all your forces. I'm going to write that sum of all forces. Okay, so in other words, F net is going to be equal to the positive force, F applied, minus any negative forces or any forces in the opposite direction. So it would be minus F friction since friction is working against F applied. So I know that there is actually an equation for the force of friction. So I'm going to replace the force of friction with that equation. So minus mu times normal force. But as we know, normal force really can just be replaced with the force of gravity since they're equal in magnitude. So let me go ahead and rewrite this equation as F net is equal to F applied minus mu times the force of gravity. But again, the force of gravity, we can just go ahead and replace that with the equation that solves for the force of gravity, which is mass times acceleration due to gravity. And at this point in time, we have all of the givens and unknowns that we need. So let's go ahead and substitute. F net is going to be equal to F applied, which is 10, minus mu 0.5 times the mass 1.2 times 9.8, which is the acceleration due to gravity. So if I solve this out, it's going to be F net is equal to 10 minus 5.88, and F net is going to be equal to 4.12 newtons to the right since it's positive. I hope that this video explanation of the different calculations was helpful. If you have any questions, please feel free to let me know, and I'll see you later. Bye!